Hello, my name is Jessica Reed, and I am a geologist with the U.S. Geological Survey Earthquake Science Center in Menlo Park, California. Today, I'm very pleased to talk with you about tsunamigenic landslides. First, I'd like to talk a little bit about subaqueous landslides and where they occur, what makes them different from landslides that occur above water. Then we'll go on to talk about tsunamigenic landslides and some tsunami hazard mitigation practices in general. Subaerial and subaqueous landslides can be a little different. Subaerial landslide refers to landslides that initiated above water, whereas subaqueous landslides refers to those that initiate below water. Subaqueous landslides can be different from subaerial landslides in that they have the potential to be faster, bigger, and accelerate more quickly and travel longer distances. This distance is called run-out distance. There are a few landmark cases of rare but giant submarine landslides, including the Storego landslide that I'll get to later. However, more frequent submarine landslides are smaller debris flows and turbidity currents. Subaqueous landslides are dominated by these debris flows, turbidity currents, and density flows, which are watery, low density, and feature very long run-out distances. Liquefaction in subaqueous landslides is a topic of research in the field, as these failures often cause the sediment to completely lose its strength and flow like a liquid with very high mobility, much like liquefaction is observed on land. So one example of a huge subaqueous landslide is the Storego slide off the coast of Norway. The slide itself is about 95,000 kilometers, which is about the size of Portugal. The volume is very big and hard to visualize, but one researcher named Bondevik and others suggest that you imagine the entire United States covered in about 30 centimeters of sediment. The back wall of this slide is 300 kilometers long, and the name Storego actually means big edge, as it was known for centuries for its cold upwelling and good fishing. The runout is also very long, characteristic of a submarine landslide, about 810 kilometers. Most of it is very low angle, 0.3 to 2 degrees, and the sediment was very fine-grained glacial deposits and silty clay. The slip plains of Storego are characteristic of passive continental margin subaqueous landslides in that they occur generally in single sediment layers for long distances. It's proposed also that this slide occurred retrogressively, meaning it started farther downslope and then crept upwards, much like you might see in a sand dune. This is a commonly observed feature of many subaqueous failures. So what causes subaqueous landslides? Just like landslides on above water, it's a fight between the resisting forces and gravitational forces. Underwater, a lot of this involves sedimentation, gas emissions, earthquakes, erosion, wave loading, glaciation or deglaciation, and even diapirs. The Storego slide, which occurred about 8,000 years before the present, is thought to be caused by climate changes and changes in sedimentation. Canyons and debris flows can be found at practically any continental margin. This is a canyon off the coast of California that shows evidence of many landslides and slumps that occurred over time. This is an interesting map. It's showing sediment thickness. And you can see that passive margins and large deltas are areas with the thickest sediment. Passive margins have their own kinds of landslides that are characteristic. These landslides are large and feature bedding parallel failure, much like the Starega slide. The failed section is usually 10 to 100 meters thick, and the same layers tend to fail over large distances. These layers tend to be very fine-grained sediments, and debris flows and long runout are very common in these circumstances. Interestingly, subaqueous landslides can also occur in lakes. There are some historical accounts of subaqueous mass movements in Swedish lakes. One in 1601 in Lake Lucerne, which is what we see in front of us. It caused a 4-meter tsunami. Another one in 563 AD was a tsunami on Lake Geneva, triggered by a massive landslide that caused widespread devastation, loss of life along the lakeshore. However, this last landslide was most likely caused by a subaerial failure on a mountain and the resulting material falling into the lake. But you can see in this survey of Lake Lucerne numerous debris flow deposits and exposed sliding surfaces, as well as many headwalls that are evidence of many failures underneath the water surface. This is a diagram of Hawaiian island chain and its deposits. You can see slumps in the dark speckled gray, and also debris avalanches surrounding many of the islands. These slumps and debris avalanches, especially the slumps, have been known to cause devastating tsunamis. The study of subaqueous landslides has in large part been motivated by tsunami hazard assessment. This is a chart showing the causes of tsunamis up to 2013, according to the NOAA NGDC database. Landslides are not evidently the most observed cause of tsunamis. According to the 2013 data of the NOAA NGDC, landslides alone cause only 3% of tsunamis. And landslides in combination with volcanoes and earthquakes cause less than 5% of tsunamis. So, as we understand it today, landslides are a major contributor to only about 8% of tsunamis. Maybe for this reason, but submarine landslides have historically been given less attention than earthquakes when it comes to tsunami hazard. As you can see, earthquakes make up 81% of tsunamis. It should be noted that it's much more expensive and time-consuming to observe landslides than it is to observe earthquakes, and can almost never be done in real time, in contrast to the abundance of seismic stations and near instantaneous seismic data. However, landslide tsunamis have been observed as more locally destructive than earthquake tsunamis, which makes them well worth studying. It's been 7 years since Harbits analyzed this information from the NOAA NGDC database, so I decided to pull an update. Here on the left is the most recent cumulative information about world tsunamis. And on the right is the 2013 information from Harbits et al. You can see that the distribution is pretty much what it was 7 years ago. I should note I didn't include explosions or questionable earthquakes, so the percentages might be a point off. A few percentage points since 2013 have been lost to earthquakes and a few gained to landslides, as well as more unknown causes. In Indonesia, however, the same database attributes more tsunami events to volcanic activity in yellow compared to the world average, and the unknown causes in Indonesia reaches 9%, while landslides are less than 1% of the observed causes, and landslides play a role in only 4% of tsunami events overall. Remember that tsunami data is not at all robust, and since landslides are often underrepresented as a cause of tsunamis, it's possible landslides could have generated a lot of the tsunamis that are listed with undetermined causes. Again, landslide tsunamis have been observed as extremely destructive locally, and so it's important to take them into consideration even though they represent such a small percentage. This map shows tsunamis in Indonesia that were generated by volcanoes or volcanoes in conjunction with another hazard. One example is the 1883 eruption of Krakatau, which was a devastating event, killing an estimated 36,000 people with associated tsunamis, pyroclastic flows, and ash. It completely changed the immediate geography. And there are competing hypotheses about what actually caused the eruption, whether it actually was a slump, so a combination of volcano and landslide activity, or an earthquake perhaps, or simply subsidence. This is a map showing tsunamis involving earthquakes, and as you can see, the majority of these events are attributed solely to earthquake activity. One example is the recent 2004 Indian Ocean tsunami. This map shows tsunamis caused by landslides. Lembata 1979 is the only yellow dot, meaning the only event that was attributed solely to landslide activity. In fact, this landslide was subaerial, meaning it started out on the coast and fell into the ocean. The resulting tsunami had run-up heights of 7 to 9 meters and flooded inland as far as 1.5 kilometers, killing 539 people. The fact that it was a subaerial landslide means that it was more measurable and visible. This shows tsunamis with unknown causes. A lot of these incidents occurred in the 19th and 20th centuries. The most recent event was 1929, when during an ebbing tide, a very high breaking wave killed 6 people by capsizing the boat they were on. It's possible that this event was caused by a submarine landslide, but in general, many of the events of unknown cause were very small and old, emphasizing that really accurate data on tsunami events is quite recent. Some well-studied events feature interrelated causes, such as Palu 2018 earthquake and tsunami event and the Anak Krakatau event in 2018. On December 22, 2018, Anak Krakatau erupted and partially collapsed, causing a tsunami that killed more than 420 people. The tsunami is widely attributed to the flank collapse landslide caused by the volcanic activity. In Palu, the fast tsunami arrival and multiple wave directions, along with high run-ups, suggest that several landslides influenced the tsunami behavior. This is an interesting study that examines tsunamigenic landslides in Indonesia, shown as red circles. Geophysical evidence of landslides is shown by white circles, some of which may have triggered landslides and could be studied further. This brings up a question that researchers are really asking. Were some of these tsunamis with unknown causes actually triggered by landslides? In 1998, a moderate magnitude 7 earthquake occurred off of the north coast of Papua New Guinea, near Aitape, just 130 kilometers south of the border with Indonesia. A large tsunami was generated and arrived at the nearest shore about 20 minutes later, affecting only 25 kilometers of coastline, but with run-up heights between 10 and 15 meters. Tidal gauges in Japan recorded the tsunami, but at that point it was only 25 centimeters tall. Locally, it was a very devastating event that killed more than 2,000 people. This event surprised everyone. According to existing models, the tsunami was too large and arrived too late to be caused by the displacement of the earthquake. This motivated scientists to investigate whether a submarine landslide might have contributed to the tsunami. These bathymetric surveys, shown here, helped scientists more accurately model the tsunami event with a slope failure origin that was triggered by an aftershock of the earthquake. This realization that landslides, particularly slumps and slides, that can occur in tectonically active zones can actually generate extremely dangerous tsunamis, especially to local areas. The slump was determined to have a volume of 6,400 cubic meters. The earthquake event in Palu generated tsunami waves in different directions. This sparked scientific interest in possible landslide contribution to tsunami generation. These white lettered boxes on the right of this study indicate areas where coastal retreat was observed after the tsunami. These are all near estuaries. These areas of coastal retreat could have caused local tsunami amplification. The images on the left show a closer aerial photos from box C of the figure on the right. The top one shows before the event and the bottom one shows after the event. The white line indicates original coastline and the red line shows the estimated maximum extent of the tsunami. This was an interesting study recently done also on Palu. A combination of observed and hypothesized landslides were simulated to fail. Up in the upper left figure, you see the failures marked L are simulated or hypothesized landslides, rather larger for the purposes of this study, while the failures marked S were actual observed failures after the event. The resulting modeled tsunami was compared to observations of the actual event. You can see the different waves interacting with each other. These simulation snapshots are 1 minute apart, creating a complicated pattern of wave heights in the bay. This study is interesting because it not only observes the role of these smaller delta landslides in creating tsunami waves, but it also proposes that larger landslides might have occurred away from the shore, actually generating the tsunamis once failure was triggered by the earthquake. So this is another example of how modeling is helpful, not just for visualization, but for generating estimations on arrival time and wave height. This is a video from the Australian Bureau of Meteorology's National Tidal Center of the 2004 Indian Ocean earthquake and tsunami. It's a 24-hour time lapse showing how the wave traveled throughout the world. Post-tsunami modeling ideally helps us to more accurately forecast tsunamis the next time before they reach the shore. This is especially urgent in Indonesia, where many tsunamis are generated very close to shore, giving almost no warning time until wave arrival. Tsunamigenic landslides have, in some cases, been identified as a major contributor or cause to the tsunami, but these events, particularly submarine landslides, are extremely difficult to detect and monitor real time. This is why landslide tsunamis, for the large part, cannot be forecast. However, most tsunami early warning systems are based off a much more abundant and detectable data source, which is seismic activity. Seismic activity accompanies most tsunamigenic events, whether it's ground displacement near a subduction zone, a volcanic eruption, or even a landslide, which can emit low-frequency seismic waves. Another part of tsunami detection is measuring the wave heights. The picture below shows the height of the sea surface in blue, or measured by a satellite 2 hours after the initial earthquake hit the region south of Sumatra in 2004. The data were taken by a radar altimeter on the satellite. The data shown are differences in sea height from the 20 to 30 day period before the tsunami earthquake, showing basically the heights of the tsunami. Another way that tsunami wave heights are detected is on the ground with coastal tide gauges. Coastal tide gauges were first designed to record lower frequency events like lunar tides and seasonal tide changes. Therefore, the sampling frequency was about every 6 to 20 minutes for digital devices. This works great for tides, which have about a 12.5-hour period, but it's too long for accurate tsunami detection. The 2004 tsunami actually really changed this, and modern tide gauges sample every 15 to 60 seconds, which is sufficiently high frequency to accurately detect tsunamis. But this also means that in terms of data collection, we only have about 15 years of really solid data. And when you compare that to the average of 2 tsunamis a year, that's only 30 data points. This is a reading from a tide gauge in Seychelles of the Indian Ocean tsunami wave. And you can see here the normal pattern of a lunar tide compared to the dramatic tsunami wave arrival. Another way of measuring sea level height is in the deep ocean. The Deep Ocean Assessment and Reporting of Tsunamis Project, or DART, was started by NOAA in 2001 as an array of 6 buoys. Today, several other countries have similar buoys. Australia, in fact, has 2 in the Indian Ocean that detect tsunamis hazardous to Indonesia. There are about 60 similar instruments in operation around the world, which all go by the common term tsunometer. These instruments use a bottom pressure monitor to calculate the height of the water column above them. The BPR is shown in this diagram on the bottom left. The BPR then transmits the information to the buoy with acoustic waves, and the buoy transmits the data to a satellite. This is a reading from tsunometer station 56001, which is actually one of these yellow triangles on the map in the Indian Ocean. It's run by Australia, and this week recording shows a normal tide water levels. When a possible tsunami wave or any water height event is detected, the rate of the data collection will increase. The normal rate is 15 minutes, but once the BPR detects something unusual, it will begin to collect information at 1 minute and then 15-second intervals in order to record the tsunami as fully as possible. There are some limitations to this kind of tsunometer. First, they must be in the deep ocean where coastal disturbances of the water like wave reflection don't interfere with measurements. This makes them less ideal for very near-field tsunamis, like the one in Flores in 1992, which arrived onshore only 5 minutes after ground shaking. However, tsunami waves actually travel faster in deep ocean, so tsunometers may detect the tsunami before a coast gauge does. Another drawback is that these tsunometers must be maintained every few years, which can be expensive. Additionally, there are just very few of them, which is insufficient coverage for many areas. One thing I'd like to point out on this record is the amplitude of this tsunami recording is very small because it is in the deep ocean. A tsunami in the deep ocean would have a long wavelength, but a small deep water tsunami wave amplitude, H. Because of this, it can travel very fast, about 1,000 kilometers per hour. Since the speed at which a tsunami moves depends on the depth of the water, when the tsunami reaches shallower water, it will slow down. The tsunami wave behind it is still moving fast, and this fast-slow difference causes the wave to stack up. As the wave energy gets squished together like this, the height of the wave increases. So even though a tsunami might have a height of several meters on land, it could have the height of less than a meter in the open ocean. Cable bottom pressure recording systems have been implemented in Japan, Canada, and the US. They provide power to the BPRs with the cables and take data directly to an onshore station instead of using satellite, which cuts the transmission time to less than 1 second. It also eliminates the need for a buoy, which is vulnerable to harsh weather, accidents, and even theft. Plus, you can get a dense array of detectors compared to standalone tsunometers, and this allows you to more precisely assess the direction and speed of the wave arrival. This diagram is of Japan's dense ocean floor network system for earthquakes and tsunamis, otherwise known by its acronym DONET #1, off the coast of Japan. It includes pressure monitors and strong motion sensors, broadband seismometers, even hydrophones and thermometers. Installation of this particular network began in 2006 and was completed in 2011. DONET 2 is in the process of implementation now. One drawback of this system is that cabled BPR systems are more expensive initially than buoy tsunometers. But they also don't require the same kind of upkeep, and so cost is expected to even out over time. A very new idea is the smart cable, which would basically attach all previously mentioned instruments to telecommunications cables seen in pink as they are eventually replaced. The figure behind shows the cables that have the capacity to be upgraded into smart cables eventually. One upside is that these cables are already a part of our systems. Adding the sensors would simply expand their function to include tsunami wave detection. The figure on the bottom left shows a sketch of what the sensors would look like attached to the cable. And a particular concern or area of focus in this project is that if the tsunami detecting instruments fail and break, it must be allowed to break without the failure of the telecommunications cable. So all of these measurement instruments are used in tsunami early warning systems. This is the basic outline of a tsunami early warning system focused on Indonesia's INA2s. First, an earthquake would be detected. And while the information, the seismic profile of this earthquake is being generated, a basic hazard determination would take place. This involves a quick seismic analysis, dip, strike, and magnitude. Also, a query would be run through the Tsunami Early Warning System Scenario Database, which is a database of simulations and earthquakes, tsunami scenarios, categorized by the fault zone that they're on. So for example, these green dots represent the Sunda zone. Any earthquake that occurs along that would be run against the Sunda zone scenario database. This would give a general forecast of what kind of tsunami response is expected. Since Indonesia is at risk of tsunamis with sources incredibly close to the shore, the time between earthquake detection and tsunami arrival is very short, and therefore initial warnings rely on this immediate information from the scenario database. After this, or really at the same time, real-time modeling takes place. This is based on the seismic analysis of the specific earthquake that has just occurred and the focal mechanism that has been determined. Real-time modeling is conducted to determine estimated arrival time, estimated inundation, and maximum wave height. This is also done in areas that are not covered by the scenario database. In the case of the Indonesian early warning system, this real-time model is called EasyWave. Eventually, the tsunami wave will be detected by water level instruments, including tide gauges and dart buoys. This data will help to refine parameters that will go back into the real-time model and improve the accuracy of the information. This loop will run several times as the tsunami propagates to provide more accurate information to warning dissemination. This is a close-up of the scenario database showing the different fault zones and all of the areas that are covered. This is just a couple of, more than a couple of examples of tsunami numerical simulations and models that have been used. I encourage you to look at these on your own time if you're curious. They have different advantages and drawbacks based on what depth of water is being examined, what kind of earthquake is generated, and whether you are looking at a landslide contribution or not. Finally, there are always going to be new directions for tsunami research. The green lines in the lower left represent some ship tracks. There have been projects and there are ongoing projects with ships that have GPS instruments aboard, which can detect water heights to a precision that allows for the detection of tsunami waves. Another area of research is on the upper left is the WERA HF radar antenna array in Oman, which is supposed to detect tsunamis as well. Of course, a very hopeful area of study is also the smart cables.